At a few minutes past, hello everyone, and thank you for coming. Welcome to our tutorial on property-based testing. My name is Hatfield-Dodds, and over here, my colleague Brian Soklaski. We're both maintainers of the property-based testing library Hypothesis, and pretty excited to share more about how you can use it with you today. So the plan is we're going to go through 4 parts of this tutorial, and we've got exercises for parts 2, 3, and 4. In the first, we're going to talk about basic property-based testing, starting with, for example, what is property-based testing? Hands up who already has a good idea about that. No? Okay, this will be an important section then. Once we talk about what property-based testing is, we'll start talking about how to describe the data that you want to test with, common tactics for using property-based testing, and then we'll finish with a section on putting it into practice, which is the kind of tips that take you from like the exercises that you're going to be doing today to actually applying it at work or in open source projects or in a larger kind of realistic context. So, property-based testing at kind of a 101 level. I'm just going to start with the testing part of this. My favorite definition of testing is that it's the art and science of running your code and then checking that it did the right thing. So there are a lot of cool ways to make sure that your code does the right thing that are not testing by this definition. Things like putting assertions in the main code, using a type checker or linters like flake8, getting one of your colleagues to review your code, drinking coffee, or perhaps getting a little more sleep the night before. All of these are great ways to improve the quality of your code or find bugs, but they're not testing. So that's the last you'll hear of them from me today. And there are a lot of different kinds of tests that we might use. One of my friends, Hillel, wrote a big list, and some of them include things like unit tests, integration tests, snapshot tests, where you record the output of your code and then can later check that it didn't change when you changed your code. You can parameterize tests. Hands up who's used PyTest before. Keep them up if you've used a PyTest parameterize. Okay, about half the room. You can have fuzz tests, and fuzz tests basically throw random data into your function or your code to try to make it crash. You can have property-based tests, which is what we're talking about today, and then stateful model-based tests, which are like a fancier form of property-based testing that we will not be discussing in depth. So to start off with, I want to talk briefly about examples. Our friend David says every time someone uses reversing a list twice, which should give you the original list, every time someone uses this to demonstrate property testing, he takes a drink. It's not a drinking game, he just doesn't like this example very much. Let's make the most common example in blog posts a non-generalizable property of a function that's almost impossible to get wrong. Who here has ever had to implement code to reverse a list? No one? Yeah, so maybe one. It doesn't come up very often, and honestly, it's not why we think property-based testing is important. So let's talk about sorting instead, which, hands up who's implemented a sorting function ever. Okay, quite a few more people than reversing. So this is a real-world kind of problem that we might have. But it's also a good demo. So traditional unit tests, we might write a couple of tests that our sorting function gets the right answer. If we sort 1, 2, 3, we should get 1, 2, 3. Yeah? Okay, good. If we sort 3, 2, 1 as floats, we should get 1, 2, 3, but this time the output of floats. Still with me? And it's not just numbers. We can also sort strings. Anything we can compare, we can sort a list of. Right? Does this look like a good test suite? It's not a bad test suite, but it's not exactly comprehensive, right? So you might just want to make this a little simpler to maintain and go, that's too much code, so let's use PyTest. We'll use this parameterized decorator and just be able to write out a table of the inputs and outputs. And this has a big advantage. It's much easier to add new test cases to this one compared to writing the whole test again. Admittedly, there's not that much setup code for these tests, but in realistic cases, parameterized can often be a big improvement. But there's still a bit of a catch, right? We have to manually work out what are good input values and then manually work out what's the corresponding expected output value. And we could get that just by running our code and seeing what it does, but then we're kind of testing that our code does what our code does, which sometimes that's the best option available, but sometimes we can do better. For example, if we have a trusted sort function, which for some reason is not Python's built-in sort function, we could just come up with the inputs and then assert that our sorting function gets the same result as a trusted sorting function. Can anyone think of a case where you might have this kind of pattern in practice? Who ever refactors code? So you have the old version and the new version. Or you might have multi-threaded code, and you can run it with one thread or with many threads. So this pattern of being able to check your results against a trusted implementation, it doesn't have to be a completely independent implementation. It can be last week's version, the single-threaded version, sometimes a really slow and stupid version, which you're confident is correct, but it's too slow for production. So that's a pretty useful pattern, but you still have to come up with the inputs yourself, right? And how do you know that you've covered all the edge cases? Kind of by definition, you're unlikely to discover an edge case that you didn't think of by writing this kind of test. And so if we don't have a trusted implementation, we can still check some things about the outcome, right? We can sort our argument, and then we can check that if we look at each pair of elements in the output, that they should be in non-decreasing order, right? This test should pass for every valid sorting function, right? Is it a complete test? Any problems with it? Yep. Indeed. This test would pass if sorted returned the empty list for every input, which is maybe not quite what we wanted. So we could add an extra couple of checks. We could check that we have the same number of elements in the input and the output, and that the set of elements is the same. Is this a complete test? No? What's the problem this time? Yeah, so you could go from 112 to 122, and that would not be a valid sorting function, but it would pass this test. Okay, so what about this one? So we have the same ordering check as before, but then we say that the result has to be a permutation of the input. Is this a good test? Maybe? It's a bad test? Why is it a bad test, Ryan?
First of all, that permutation might get real expensive.
Yeah, this could be incredibly slow. So I guess it's a fine test if your lists are like of length up to 4, but in production, it's not going to work very well. So if we import collections.counter, we can say we have the same number of each distinct element in the input and the output. What do we think of this test? You've all become terribly cynical and untrusting in the short time that we've known each other. You could be modifying the inputs. Yeah, so if you have mutable inputs or mutable elements in the input, that could be a problem still. But if you don't, I think this test is actually pretty good. Right? This is how I would write a property-based test for the sorted built-in. So we've just written 2 properties, and that's the properties in property-based testing. The first property is that the output has to be in order, and the second property is that you have the same elements in the input and the output. So this is what we call a complete specification, right? These 2 properties are sufficient to identify a correct sorting function. But partial specifications, even if we only checked one or the other, there are still many bugs that we would have found, right? Even that earlier test where we just checked that we had the same length and the same set, this would find most plausible bugs, right? If someone is not trying to sneak an evil sorting function past you, this test is pretty good. So the generalization is, hypothesis is a library to help you come up with the inputs to this kind of test to discover the edge cases that you hadn't previously thought of. And so in this case, we can say, instead of writing out that list of integers and floats and strings, we can say that given an argument which is one of either lists of some mixture of integers and floats, right? So it's okay to sort a list that combines integers and floats, but you can't combine integers and floats and strings. So we'll say it's a list of either numbers or of strings. And then we have the same checks. This test actually turns up an edge case that we hadn't thought of, because floating point not a number compares unequal to anything else. If you compare nan to any other number, is it greater than x? False. Is it less than x? Also false. Is it equal to x? Still false. And so the behavior of sorting a list which contains not a number gets remarkably more difficult to specify than you would have thought. So I like property-based testing partly because it teaches me about the language and the libraries that I'm using by checking my guesses about how they behave. In this case, though, we're just going to tell hypothesis, look, I just don't want to hear about nan. That's too complicated for a tutorial example. I'm not going to put that on a slide for you, so just exclude those examples for me. I only want the well-defined comparable numbers. So to summarize, right? We've looked at property-based testing. It helps us generate input data that we wouldn't have previously thought of. And the key idea is that we can check that the result is not incorrect. Even if we don't know how to calculate what the result should be, just checking that we didn't get the result that we can tell is wrong in some way is enough to find an awful lot of bugs. And those bugs can often be in our, or at least my, understanding of the code I'm using, the code I've written, the language, the libraries I use. And in some cases, though I didn't show this, you don't even need an assertion in your test. I like putting lots of assertions in my code to check that something I think is impossible hasn't actually happened. And then generating weird input data and feeding it into your test can often trigger those assertions, or just a plain error in your code somewhere, where you hadn't handled an empty string or an empty list or an infinite element, for example. So with that, we're at the end of the first of 4 sections. We're going to take 5 minutes now to go to this link, r/testing tutorial, and get that set up. You can either install all the dependencies locally and run things on your own laptop environment, or we have clickable MyBinder links which will open a notebook in the browser for you if installing things becomes difficult for some reason. In 5 minutes then, we'll come back and go through part 2 of the talk on describing data.
One thing to note.
So, can I see a quick show of hands? Who has Hypothesis installed locally? Okay. Who would like a minute more to install Hypothesis? Okay. I will trust that you can install while I'm talking then. So let's jump into part 2 of 4. So I think I actually missed describing the math structure. We've got 4 parts. We're going to run through the first part, which we've just done, then install things, which we've just done. Part 2, we'll give a short talk and then have some meatier exercises using the tools you've just installed. Then we'll take a quick bio break for people who like things like coffee or bathrooms or stretching your legs. We'll come back and have another pair of short talk and exercises, short talk and exercises. And through all of the exercises, Ryan and I will be around to answer any questions you have about the exercises or about Hypothesis generally. So the second part, now that we know what property-based testing is talking about how to describe the specific data that you might want to generate using a hypothesis. There are a number of different kinds of what we call strategies. Strategies are those things like the lists and the floats that I showed you, which describe what the data should be. Hypothesis comes with built-in strategies for things like scalar values, the various numbers or strings that you might want to generate. For collections, where you can say, I want lists where the elements are drawn from some other strategy, or I want sets or tuples or dictionaries. You can modify strategies with the map and filter thing, and there are a variety of special cases that we'll walk through with specific slides. Exercises at the end of this part, we're going to be focusing on generating data rather than asserting particular properties of your code at this point. So for scalar values, scalars like individual elements. Hypothesis has built-in strategies for none. That one's very simple. It just generates none. The Boolean strategy can generate true or false. So we're getting more complicated. And then once you get into numbers, we have integers. There are floats where you can specify the range, whether or not to allow infinite numbers, whether or not to allow nan. For floats, you can also specify bit width. So whether you want 64 or 32 or 16-bit floats. You can generate strings, whether individual Unicode characters or the string type or bytes, dates, times, time zones, and very many other things. I believe it is literally the case that if you can name it in Python, you can generate it with Hypothesis. So let's look at a short example. This is one of those simple patterns that I talked about earlier. We're going to look at the binary or not library, which is on the Python package index. It has an isBinaryString function. And so what we're going to do is say, given any binary string, this generates instances of the bytes type. We're just going to call isBinaryString on that, and if it crashes, then we'll know we have a bug. What do we think is going to happen? It'll work perfectly? Well, it would be nice if that was the case. But in this case, not even asserting and just calling things can be sufficient to find bugs. So this one has since been fixed, in fairness. But what happened was that binary or not internally used the chardet library, which tries to detect character encodings. And chardet looked at the first few characters of a randomly generated binary string and said, oh, this looks like it's UTF-8, or whatever the encoding was. And so based on that, it returned a 100% confidence rating. But as documented, there was no implication that a 100% confidence meant that this was actually a valid string for that encoding. Which may be a little confusing, but it was documented. And so what we found here was a bug where the authors of the binary or not library had misunderstood the return value from this other library that they were using. And that could cause a crash on some particular weird inputs. Let's look at something a little different. Who's heard of the Mercurial project? One person? It's a version control thing which competed with Git for a while, implemented in Python. And so it has these two functions, from UTF-8b and to UTF-8b, which encode bytes in Unicode. And so the test that we're writing here is, given any binary string, if we convert it to UTF-8b and then from UTF-8b, we should get the original string back. Seem reasonable? Can anyone think of a case where you might apply this to your own code? Some of us? You'll see more of this soon. Unfortunately, we find another bug here. Again, this was found using hypothesis, reported upstream, and fixed quite promptly, where it turned out that this particular weird sequence of bytes would lead to a crash. Okay, so what about date parsing? Who here loves working with times and dates? No? I can tell from the laughter that some of you have had to before. So what we're going to do here is we're saying, give me an arbitrary date time. I will format it using the ISO format method, which gives you the nice 4-digit year dash 2-digit month and so on. And then what we're going to do is we'll check that our formatted string is the same as parsing the formatted string and then formatting the date time that we get from that. So we're comparing things as strings rather than date times here just to avoid any particular weirdness. That's not really necessary. And what we find is this completely bizarre bug that brought joy to the lives of several maintainers a few years back, where it turns out that this failed if the year and the month, it would swap the year and the month in the parser if and only if the year was between the year 0 and the year 9 and equal to the number of seconds in the date time. Do you think you would have caught this without hypothesis? Because I've got to admit, I'm kind of surprised we caught it at all, ever. But here we are. Okay, so that's what we can do just generating individual elements, scalar values. If we're generating collections, this gives us the ability to do more complex data sets. We can have lists of any particular thing. And for lists, you can say what the minimum and the maximum size should be, and whether you want it to be a unique list or unique by some key function or group of key functions. You can have tuples, where you say, I want a tuple where each element is drawn from the corresponding strategy. Or you can have dictionaries where you say, give me a dictionary where each key has a value drawn from the corresponding strategy. So this is pretty useful as well. To look at that, we might test, given some list of floats, which is non-empty, we're going to test that the mean is between the minimum and the maximum, inclusive. Right? We have to specify min size equals 1, because the minimum function will just raise an error on an empty list. So what do we expect to happen here? NaN could be an issue, yep. But in this case, what we're going to see here is if we have two very large values, it seems like mean is probably implemented by adding them together and then dividing by the length of the list. And what we found is if we pick two very large floating point numbers and add them together, we get infinity. And then when you divide infinity by 2, you've still got infinity. And so the mean is now larger than the maximum. It turns out there is an entire field of research on numerically stable floating point algorithms, which do not fit on one slide. So mean is harder than we would think, and the standard library mean function turns out not to be stable in this way. So much for collections. The next two things which you'll probably use all the time if you start using hypothesis is the map and filter methods on strategies. So what map does is it draws an example from that strategy, and then it applies the function that you provide. So for example, if you have integers.map str, this will generate an integer, then call string on it, and generate the strategy with the map will generate strings that were created by calling string on those integers. And filter, conversely, lets you reject kind of weird or bad inputs. So the idea is you can provide a function which returns false or a falsy value if the example that was drawn is one that you don't want to test. So for example, you might say, I want integers but not 0 because I'm testing division. So you could write integers.filter lambda x not equal to 0. And that would give you random examples, but rejecting those that didn't match. So here, for example, we might want a pair of integers which is in ascending order. And there are two ways we could do this, right? We could do it with a filter, saying if we have this lambda, we want xy such that the 0th element of xy is less than or equal to the second element. And that will work, but it will work by rejecting about half of the examples, right? So we'll draw random examples, and some of them will be in the wrong order, and we'll throw those out and try again. This works pretty well in practice, but it's more efficient if we just map sorted, which just swaps them if they're out of order. And then in this case, because sorted returns a list, we can map tuple to turn it back into a tuple afterwards. Does this make sense to people? Cool, I'm getting some nods. A couple of special strategies. I realize I'm just kind of info dumping on you. That's why we have the exercises. A few special strategies. Just is for when you have a value, but you need a strategy for the API. So for example, the datetimes strategy has a time zone argument, but the time zone value that you pass has to be a strategy. So if you always wanted your time zone to be in UTC, you could pass time zones equals just UTC. And the just strategy pretty much does what it sounds like. It just generates the value that you fed it. Sampled from is great if you have a couple of different alternatives. Say you wanted your join to be either an inner join or an outer join. Well, sampled from will generate random selections from that list for you. This also works well with the nums. So if you have something like permissions, it will also generate combinations of those values if you have an enum flags type. When you want to combine strategies, one of is just the union of those strategies. So we saw this way back at the start, where we wanted to generate integers or floats, or lists of integers or floats, or lists of strings. That was using the one-of strategy. And then nothing is kind of special here. Nothing is a strategy that can never generate anything at all. You might think, what is the point of having a strategy that can never generate anything at all? It's pretty useful when you have, for some reason, an API where you have to return a strategy which you're going to use one of with. And basically, we'll just skip over that because we know there are no elements in it. So one of integers and nothing is just the same thing as integers. Unfortunately, you can't take the intersection of two strategies. So you can't say, only give me values that either of these strategies could generate, because that would require us to understand whatever map or filter functions that you put on it. And you can't generally subtract them. So give me everything from this strategy unless it could be generated from that strategy. It's just not feasible in general. Okay. Are you following so far? Raise your left hand. Okay, so most of you are still awake. The builds function is the next useful kind of strategy. Who here ever defines their own classes? This will be useful for all of you then. Builds is how you tell Hypothesis how to make an instance of some arbitrary class, or function, or other callable. So you could think of it as basically error handling and some syntax sugar over the map function, where you could generate instances of your class by generating a tuple or a dictionary of all the arguments you need, and then mapping with the constructor of your class. But builds is a little more ergonomic. You just pass it the thing that you want to build, and then positional and keyword arguments, which are strategies, and then we build you instances of those things by generating values from those strategies and passing them as the corresponding positional and keyword arguments. Builds will also do type inference for you. So if you have type annotations on your code and you don't pass a strategy for a required argument, Hypothesis will just look at the type annotations and work out how to make one for you. Ryan's a fan. It is remarkably convenient. You can just say, give me instances of foo, and it will look at foo, and if foo takes a bar, it will work out how to make a bar and then pass that to the foo for you. Who here has ever dealt with recursive data? So trees, for example. At least two of us, maybe more. Okay. This is a little more tricky to express. So there are a couple of different ways that hypothesis gives you for describing recursive data, because each of them will be more natural in different contexts. The first is that we have this recursive strategy. And there you give it a strategy as the base case, and then a function which takes an object and returns a strategy based on that. This is like your base case and then your extension. And so for things like JSON, this is remarkably nice. This is, by the way, a complete definition of a hypothesis strategy that can generate any value representable as JSON, which is pretty nice. Or we have the deferred strategy, which lets you define mutually recursive functions. My rule of thumb is use that whenever you get a name error, where you're trying to refer to something that hasn't been defined yet. The last nice thing here, or not the last nice thing, another nice thing, is that hypothesis can often infer strategies for you, because writing things out by hand is kind of tedious, and I feel like against the spirit of Python. So from type, I mentioned, is built into the builds strategy. So if you have a type annotation, it can just automatically work out what to call there. You can also call it on a particular class or type for yourself. And so inference is designed to be a time saver. It will almost always pretty quickly work out something reasonable for you, but sometimes that will permit more possible values than you actually intended. And in those cases, you can write a strategy by hand, even just specifying the particular bits that you want to be different and inferring the rest. We also have this register type strategy function. This one is so that you can customize. So if you have a particular class, you can customize what hypothesis will generate as a strategy for it when asked. So this is pretty useful if you use a type all over the place. Once you register it once, you can then infer it everywhere else, and the constrained strategy you define will be used. And we can infer from other things, like if you have a regular expression that you use for validation, hypothesis can generate strings that match the regex for you. Who here uses NumPy? We can also generate things based on data types or shape signatures. Who uses Django? Okay, if you have a field or a model, hypothesis will also automatically generate things that can be stored in those models for you. And in fact, stash them in database. So inferring these strategies is a really nice pattern to save some time and generally make your testing more ergonomic. If you're implementing your own inference, which you probably will do once you've used hypothesis for a little while, try to err on the side of inferring the most general strategy that could generate the widest range of possible inputs. Because in my view, the worst kind of problem with tests is the missed alarms, the tests that just didn't check the edge case that turned out to be a bug in production. So I'd much rather spend a little more time when I'm writing my test to make sure that I'm actually covering all of the edge cases that I can think of. And then the last tip, which we've tried to follow here, is to make sure that there's a really smooth path from just letting you say, hypothesis, work it all out for me, to then saying, like, hypothesis, work it all out for me, except the bar argument to a BAS needs to be non-negative. Yep. So does each strategy generate all possible permutations or outputs? We do a sort of heuristically guided random sample from that space. The exact distribution is remarkably complicated because we keep tuning it based on research, based on feedback from users, based on measurements of what your code is actually doing as we execute those tests. In practice, the search space is usually too big to enumerate all the possibilities. In many of them, it will just be infinitely large. So hypothesis, by default, will generate about 100 random samples. But if you want to, you can turn that up to 1 million and leave it running overnight. Here's an example using Django. This is a more complex test, right? So this is sort of business logic-y, and it still works. So running through it. We say we have given. This is our standard decorator that describes what kind of inputs you expect. We say from model. So we want instances of our project where the collaborator limit is between 0 and 20. And we want lists of things generated from our user model of at most 20 users. With me so far? Awesome. So we then have a test with a descriptive name, which takes a project and our collaborators list. Then we go for C and collaborators. If we're at the collaboration limit of the project, assert that adding that user raises a limit reached exception. And then check that our project team does not contain that user, right? Or, if we're not at the collaboration limit, add the user and assert that the user is in the team. Simple enough? It's not rocket surgery. And what we actually see if we run this is that hypothesis will generate a list containing 2 identical users. And then our assertion will fail, because if you try to add a user who is already in the project when you're at the collaboration limit, then you'll raise the limit reached exception, but the user will still be in that thing. So the solution in this case is that we needed to make our lists unique as well. And if we'd done that, then this test would pass. So, I think these are the last strategies that we're going to talk about before we jump into exercises for a while. Sometimes you have data which has internal dependencies. By that I mean one part of it has to have a particular relationship with another part. For example, you need 2 numbers, but they have to be equal. Or you need a project and a user, but the user has to be a member of the project. For these cases, there are a couple of ways to do it. The most elegant is usually the @composite decorator. This lets you generate functions which define custom strategies. So you put the decorator on, you provide a first argument called draw by convention, and then you can take whatever other arguments you like, whether they're strategies, other values. It's fully customizable, so you can write anything that you can write in Python. And then the draw argument is a function which you can pass a strategy and it will return a value from that strategy. This is like a little bit of the hypothesis internals ready for you. So in this case, we want widgets, and so we're saying, well, we'll pick a random factory from the locations strategy that was passed. We'll pick a random power setting, I guess, between 0 and the maximum voltage or whatever it is, and then we'll return a widget constructed using that power thing, made in the factory and with a given key. Flatmap is similar, but it's a sort of function composition style for people who like functional languages. And data is another thing again. In this case, we didn't actually need to do this validation every single time, right? We're going to pass our arguments in, but then each time we generate a value, we don't need to repeat the validation logic. So I often find this kind of a useful pattern where I put the composite on an inner function. So that's doing the minimum possible amount of work each time. When you have expensive validation, this is a nice performance tip. In this case, though, we didn't actually need composite. You can just have functions which return strategies, right? So in this case, we take our arguments and then we return builds. So we say, build me a widget where the power is drawn from this float strategy and it's made in locations and the key is just the valid key. Does that make sense to people? So all 3 of these do the same thing, right? Where we have our original composite. This is a pretty idiomatic use of composite, but we have that validation. We pull the validation out to save a bit of performance, and then we realize that we don't actually need composite at all. In this case, we can just use builds. And having custom functions which return strategies is just a great ergonomic tip, right? I really like having a file full of helper utilities for my test suite. Data is exactly the same as composite, except it works inside your test function. So the decisions about what data to draw, how to interact with those strategies, can be made based on partial results from your test. The upside is that this is the most flexible and powerful possible way to do it. The downside is that it is the most flexible and powerful possible way to do it. And that means that the error reporting, for example, is slightly more complicated because we have to show you the order in which you drew things instead of just the arguments which we generated for you. My summary there is use data if you need it, and then look at the test you've written and check whether you could think of a way to do it without using data. All right. That's the strategies that we have available built into Hypothesis. Where do you look for these? For core strategies, where there are no dependencies beyond the standard library, hypothesis.strategies. Should be easy to remember as long as you remember that they're called strategies and they live in hypothesis. For things which have external dependencies like NumPy or Pandas or Django, those are in hypothesis.extra. Whatever that library is named. So if you want to generate NumPy arrays, you will import hypothesis.extra.numpy. And then there are also a range of third-party extensions you can find in the documentation, where people, much like yourselves, have written their own packages which provide hypothesis plugins for things like generating network X graphs or pretty much anything else you can imagine. I will note, just because we list them in the documentation doesn't mean we endorse them. It just means we know they exist and we think our users may also want them to know they exist. All right, before we jump into the exercises for this part, I'd be happy to take any questions. Is it guaranteed to be deterministic? Great question. Slightly complicated answer. We'll get into this more in section 4. It's not deterministic by default, but there is a determinism setting you can enable, and we do guarantee that if we find a failure, we will cache that and replay it on subsequent runs. So you should never have the problem where it's flaky, in that like running it once fails and then running it again with no changes passes. Any other questions? Yep. Do we have more shared examples of how to write things? Yeah, so some of those should be in the materials, including in the exercises that we're about to do. So we have the master branch, where we have all of the questions and the problem sets. There's also the instructor branch, where we have our solutions to each of these. So I'd encourage you to try them for yourselves first, but if you get stuck, feel free to ask us, or if you're doing them later, you can look at those solutions as well. All right. We're going to spend the next 25 minutes or so on these exercises and then take a 10-minute break. Let's get to it.
Yeah. So for some context, what we're going to be doing is going into the notebooks. So notebook 0, taxonomy of testing.
Microphone.
I'm pretty loud to begin with. It's going to be notebook 0, taxonomy of testing. And so this is going to rewind way back to the most basic test. We're going to have a couple of basic functions, counting vowels and merging dictionaries. What we're going to do is write some by hand tests for them. Then we're going to write some PyTest parameterized tests for them. And then we're going to use some of those hypothesis strategies that Zach just introduced. So that was a rapid fire tour through everything hypothesis. This is going to go back and babysit all the way up to using the most basic strategies. So one thing to keep in mind is as you're going through the notebook, it will ask you to actually write tests in the repo's test suite so that you can run it with PyTest. So that is to say the notebooks are not fully self-contained. The notebook will ask you to go and write code in the repo. And as Zach mentioned, you can always toggle over to the instructors branch if you want to peek at the answers. Although I recommend doing that in your browser so you don't lose your changes locally. Concludes our break. Before we start with our next section, I wanted to make a couple of comments. I think first, someone brought up the fact that when they saw their test pass, they asked themselves, well, is it even possible for my test to fail? And that is a very wise thing to check. If you write a test and you've never seen the test fail, you should assume that there might be something wrong with your test. I am very embarrassed to say that I've had like an hour of writing an increasingly sophisticated tests that always pass. I'm like, I'm the best. My code is perfect. And then I realized I never actually called my function in the test. And once I called it, the most basic example failed. Just tears streamed down my face. So very good strategy is just switch that equals to a not equals and see the test fail and say, okay, I can move forward. More sophisticated is when you parameterize a PyTest test, you can intentionally include a parameter that should fail your test and then mark it with PyTest as an xfail parameter. In that case, the test will pass if that example causes your test to fail. And the test will fail if it causes your test to pass. Sorry for the confusing, but this is it's more advanced, but it's really nice because this helps you stay confident that you didn't do anything to break the test itself, which would be very nefarious.
Yep.
Second thing is, if you have...
Hypothesis has similar support, where we have this @example decorator, where you can provide explicit examples. We'll show those in a few minutes as a way of reproducing previous failures, but that also has a .xfail method on it. So similarly, you can write a property-based test and say, but here's an example input which should make the test fail.
Right, yeah, maybe you wrote a hypothesis test where you generated positive integers as an input. You could add @example -2, but with an xfail, saying this one should make my test fail. If it doesn't, there's something wrong with my test. This is really powerful. The other thing is, if you are still working on the first part of the tutorial, feel free to move at your own pace. The GitHub repo has all of the solutions with it, so don't feel the need to skip ahead if you feel like you're getting meaningful information out of continuing to work on the first part. So just wanted to put that out there.
Yep. All right. So we're about halfway through our time together, and so it is time for me to attempt a live demo. Please think kindly of me when this breaks, because it's going to break. Okay, so the thing I want to demonstrate is what we call the hypothesis ghostwriter. This was inspired by my experience at PyCon a few years ago, where I came and I was really excited. I taught a tutorial, much like this one, and I would bump into people on the hallway track, and I would say, oh, hypothesis, I've heard of that, it sounded kind of cool. I was like, awesome, what do you use it for? And they would say, well, I don't, I'm not sure how to apply it to my code. And after hearing this about 20 times over the course of 3 days, I decided that, like all software engineers believe deep down, this was a social problem that had a technical solution, where I could fix this problem in front of me just by writing a bunch of code. And so the code that I wrote uses hypothesis to write tests for you. Although in this case, we may need to... Yeah. Apparently my environment has broken, which may be relatable.
Wow, that's impressive. What is
Yeah. I don't know. So let's try using my shell session here instead. I think I have now appeased the gods of live demos.
Not so sure.
That was what we call hubris. Damn. Okay, so there we are. It's just very slow today for some unknown reason. So the hypothesis write command writes property-based tests for you. You point it to the module that you want to test, or the function within the module, and it goes off and produces those tests. in this case, we tried to write a function, a test for the sort function, which doesn't actually exist. So hypothesis helpfully told us that the built-ins module does not have a sort attribute. Try sorted or perhaps format. Well, we didn't want format. So here instead is a test for the sorted function. Let me zoom this a little more. So hypothesis sets up the imports, it writes our given spec, and it has 3 arguments. There's the iterables, which is one of either integers or text. Does this seem familiar from the previous section? So one difference is we've said, this is what I get for attempting a live demo, I guess. So we've got iterables instead of lists. So it could be any kind of iterable thing, including an iterator. But we also have these key and reverse arguments, which I didn't show in the earlier demo, because Python's sorted built-in does take a Boolean reverse flag optionally, and potentially a key function. And this just tests that if you call sorted, iterable, key reverse, then you don't get a crash. Seems pretty reasonable. So it doesn't have particular knowledge of the sorted built-in. You can also request this in unit test style. So this gives us a unit test case class, and the decorator goes on a test method, which is otherwise the same. Who here prefers unit test to PyTest? Okay, you're in for a treat then, because it all just works. Hypothesis is perfectly happy to help you write those methods instead of test functions. We can also tell hypothesis that sorted is idempotent. Idempotent meaning if you call sorted on the output from a call to sorted, it shouldn't make any further changes. And hypothesis, well, my laptop seems to be really slow right now. Yeah, there we are. It will eventually write a test that sorting is idempotent. So if we get our result by calling that, and then we repeat by calling it on the result, then our result is equal to the repeat thing. Make sense? This is a pretty general property, right? Many functions are idempotent, or could be idempotent in some cases, and you can test those with hypothesis without even having to write the test code for yourself. So here we see another kind of test, which is pretty common. We say that the AST literal eval function is equivalent to the eval built-in, right? So that is, if you call the 2 functions with the same input, they should give you the same output. And so we set up all of our various inputs. We call the 2 functions, and then we assert that they're equal. But here we actually see a problem. One takes a node or string argument. So we're passing literal eval, the node or string, and we're passing source to our eval function. So we would actually want to edit this a little. The ghostwriter is designed to give you a starting point, but it's not always complete. If we want to test for the addition operator, hypothesis can write the sort of standard tests for addition. That addition should be associative, so if we add A to B plus C, or we add A plus B to C, we should get the same results either way. That's associativity. Commutativity, A plus B equals B plus A. And the identity operator is just that there should be some value such that adding it to A gives you A. And with integers, that's 0, right? Next form of test that we can write is if we just say, I want to test for gzip compression. I don't know what the properties should be, just like work it out hypothesis, please. And so here it will actually give us a round trip test. So it will say, well, you asked for compress, and I happen to see that there's a decompress function in the same module. I bet if I call compress, and then I call decompress on the output from compress, then it should give me the original thing back. Does this seem reasonable? Yeah, it's done with a classic AI technique known as a big list of regular expressions and a couple of if statements. And this works remarkably well. Again, this is actually a template. It's not quite complete because the data strategy here is just nothing. That's the empty strategy that I talked about before. So if you try to run this, hypothesis will actually say, you haven't told me what data should be. And in this case, we can look it up in the documentation and see that data should be a byte string. And if we put in binary, then this test will run as well. Okay. Does this make sense so far? Can you imagine applying this to your own code and checking the results? You can even run it on whole modules. I'm not showing that here because you end up having to scroll a lot. But if you apply it to your entire module and just pipe that into a test file, you get a pretty good starting point for some tests. This is what you get if you check whether JSON round trips. It turns out that the standard library JSON loads function has a lot of arguments. Like a lot of arguments. So one thing here is we're just going to cut this down a bit. We don't actually care about all of them, so I've edited this. And for the object, I've put in that recursive definition of JSON that I showed you earlier, right? So the definition of JSON, according to the standard, is that it's none, a boolean, a number, or a string, or a list of JSON things, or a dictionary, which JavaScript people call an object, where the keys are strings and the values are any valid JSON thing. Make sense? So what does this test actually do when we run it? This is going to take long enough. I can take guesses from the audience. Any guesses as to what this will do? Can you outperform my laptop? Yeah. This particular test will eventually I don't know. It was fine this morning. Yeah, never do a live demo. They're just cursed. Yeah, we're not going to wait for the result here. What you would see if my laptop was faster is that if obj is nan, then of course the object and loaded are not equal to each other because they're nan. You can also go, only give me objects which are equal to themselves, and then you get a list containing nan. It turns out that Python's list comparison has a special case where it just checks if the other list is the same object as this list, and if so, it returns that they're equal, even though some of the elements don't compare equal because they're nan. Fun times. Okay. The Ghostwriter should be faster on your laptops because you won't be doing live demos. So, part 3 of 4 for this talk, and our first of 2 before the end, we're going to be talking about common test tactics. So these are ways to apply properties to your code and common kinds of properties that will often be relevant for you. I kind of divide these into properties which are applicable to most code. Almost all code bases will have many cases where you can have this fuzzing property, where you just call your code and check that it didn't raise an exception. Round trip pairs or equivalent functions most functions are not round trips or equivalent to another function, but most code bases will include some that are. For example, most of us, I would imagine, read data and then save data. Well, try saving data, reading it back, and asserting that you got the same data again. Metamorphic properties are also common, but we'll talk about them in detail later. And then there are situational properties, where just checking that your output is okay, checking things like the binary operator properties or stateful or model-based tests are also pretty useful. So again, I want to emphasize literally just calling your code with the weird inputs that Hypothesis will come up with is embarrassingly effective on my code. It finds a lot of bugs. For round trips, we saw those with the gzip example and with JSON. If you have save and load, encode or decode, send or receive, if you ever convert between data formats or do logically inverse things, these tend to be present in almost every code base, and they also tend to be really important, right? If it turns out that saving something to the database and then bringing it back gives you a different object, that is a really important bug to find out about, even if it's a rare edge case. So the fact that they're critical to our code, they also tend to be logically complicated enough, and those logic bugs tend to be silent failures. Instead of a crash, you'll just get a silent wrong result. And that, I think, makes it particularly ripe for property-based testing. So if you take one thing away from this tutorial, use Hypothesis on all of your round-trip functions. That's probably the highest priority thing. For equivalent functions, I talked about this before. If you have the single-threaded versus the many-threaded version, the old version or the new version, or sometimes things like the order in which you call functions shouldn't matter, and you can test that in fact it doesn't matter. You can also have functions which are equivalent only for some inputs. For example, functions which take any range of numbers, but if the two functions are both fed only positive numbers, then they should have the same output. You can test those kinds of things as well. Or sometimes functions are like special cases of another function. In that case, you can check that they're equivalent for those special cases. I always feel silly writing these kind of validations, but I find them really valuable as well. And I prefer to write them as assertions in my code. I just calculated a probability. Is that probability between 0 and 1? Just assert 0 less than or equal to probability less than equal 1. Is my string non-empty? Is the thing the type I expected? These give me really fast feedback when I try an ambitious refactoring and turn out to break a lot of things. Property-based testing was originally developed in Haskell, which is the first time I've mentioned that. And it's named for algebraic properties. They're pretty rare in Python code, but if they come up, they're worth testing. There's this lovely blog post from Atlassian, Programming with Algebra, which actually finds that these kind of properties are really useful for things like merging streams of events as part of their data infrastructure. So again, if you're working with that kind of code which is doing principled data transforms, these kind of things can be useful, and I'd look them up then. And then model-based or stateful testing I've alluded to a few times. It would be a full tutorial of its own to go through it in depth, but the basic idea is that instead of hypothesis giving you inputs to a test function, you have it choose which of a range of possible actions to take, as well as the inputs to each action. So this basically gives you a state machine API. State machines are very powerful, very flexible, and they're particularly good for APIs which are stateful. So for example, I use this with my friend Dimitri to build Schema Thesis, which is a tool for automatically testing REST or GraphQL or OpenAPI web APIs. You just point the tool at your schema, and it uses stateful model-based testing to work out what sequence of calls to the API should I make to try to uncover errors. Metamorphic relations are probably the most complicated kind of property I'm going to talk about. The idea is that for cases where we don't know what the relationship between the input and the output should be, we might still be able to look at the relationship between two input-output pairs. For example, we might be able to say, even if we don't know what the code should do, if we can get coverage information, we'll be able to say if we change any uncovered code, that shouldn't change the result. This turns out to be really powerful in compiler testing, because often the uncovered code triggers different compiler optimizations. And you don't need to know what the code does to know that changing code which didn't get executed should never change the result of the code that did. If it does, you have a compiler bug. You might know for some numerical code that if you double all of your inputs, the output should also be doubled, even if you don't know what that relationship should be in detail. You might be able to say that negating every element of a list and then sorting it should be the same as sorting it and then reversing the list and then negating the elements. So, in fact, the government of France has a similar thing where they used formal methods to prove that their tax code was such that any time you would increase your pre-tax income, your post-tax income should never decrease. Right? This is actually a pretty common problem where there are so many tricky interacting laws about benefits and tax rates and so on, that in many cases earning more money leaves you with less money. And they decided to use software testing techniques to make sure that that would no longer be the case. So metamorphic relations tend to be quite specific to your domain, but this idea of thinking about what do I know about the relationship between two different runs of my function, if I know something about the relationship between the inputs or between the outputs, can be quite powerful. But the bottom line here, right, is just put assertions in your code, then run your code, just on random inputs. Be careful to cover all of the edge cases with hypothesis, and then test any round trips that you have. Those ones are super valuable and often quite easy. After that, just relax, right? You have 80/20'd it. You have got, I think, a majority of the value you can get from fancy testing with a tiny fraction of the possible work. Of course, the further work to get the next bit can also be very valuable. But if you're wondering, just write your assertions, fuzz your code, test your round trips, and then relax. Any questions? Is there anything that hypothesis doesn't do that we should still use traditional unit tests for? Absolutely. Hypothesis doesn't test that you got exactly the right answer. So I tend to think most projects should have some amount of property-based tests. Typically, I think like between 20 and 80% is usually a good fraction. So I have projects at both ends of the scale. I've also seen projects like Black, for example, the auto formatter, just has one property-based test, which says, given arbitrary Python source code generated by hypothesis, Black should not crash. And Black should be idempotent when you reformat. That should not make any further changes. And so that single test has given them a lot of value. It's found dozens of bugs by now. But they decided that it wasn't worth trying to write much more specific tests. So they use snapshot testing instead for that kind of thing. In general, I would tend to think like a lot of this is kind of experience. You get a sense for your particular project and for property testing. So my serious advice is something like start by just getting every round trip that you can think of tested, and then think for a little bit about, are there properties that you think might catch bugs? And if so, test those. But don't feel that you have to replace all of your existing tests. Like, unit tests are great. They're really fast. They tend to be stable. Hypothesis is a great complement to them, but I don't think it's a substitute. Yeah, so this is, can you control the number of permutations from each strategy? We'll cover that in the final section on practicalities of property-based testing, but we have quite good support for settings which allow you to control things like runtime, the per test case deadline, and so on. Last question on this section, and then we'll jump back into exercises for a while. All right then. Let's do some exercises. In this case, I think we're moving on to it's notebook 2.
Actually, I'm curious. Did any of you already go through notebook 1, or was everyone working on just notebook 0 last time? Thumbs up if you worked on notebook 0. Great. Thumbs up if you worked on notebook 1. All right, we're doing notebook 1.
Yeah.
Great. So yeah, this will give you hands-on experience with hypothesis, is different strategies, map, filter, and some of the other patterns that Zach went over in the first part of the talk. Yeah, and it will also discuss more deeply what we mean by identifying properties to do property-based testing to complement your manual tests. So last time you wrote by hand, this string has 3 vowels. That is a manual test. Now, can you add to that? What are properties of my count vowel problem or function that I can write a hypothesis-driven test for? That's something that you'll do in this exercise.
Cool. Give this one about 20 minutes. Maybe take any questions about this, and then we'll move on to notebook 2 at the end of that time for people who want to. So I'm glad to see so many of you are still with us, still awake. No one's run away screaming just yet, which is always a good sign. So we've got about 40 minutes left of this tutorial. That's just enough time for part 4 on putting it into practice. So like each of the other parts, we'll have a short talk, time for some questions, and then continuing exercises at the end, whether you want to keep going with the exercises you've been working on for the last few minutes, or jump into the exercises specifically for part 4. So you've learned the kind of principles of property-based testing. You learned what it is, how to describe the data that you'll use, and how to recognize and apply common patterns in your own code. Beyond that, I want to talk about some of the practical tips for applying this to kind of production workloads, it always feels kind of weird to try to work out, how do I describe the tests for the systems that I use at work? Right? They're not exactly production because they're the tests, but they're not exactly examples or toy things either. So we'll talk about settings and settings profiles. We'll talk about the way that Hypothesis saves examples to replay and how you can store and manage that. And we'll talk a bit about fuzzing and also the release cadence. So one important point, which we got to in the questions earlier, is that I see property-based testing as part of a more general test plan. It's not all you should do. And the last thing I want you to believe is come away saying like, Zach says we should only write property-based tests. Not at all. I think you should write at least some property-based tests, but probably not literally all of your tests should be property-based. I see sort of 10 to 90% as being a pretty good ratio for most projects, and where in that depends on what kind of project it is. One neat tip is design custom strategies for your particular project. They're great as a single source of truth for what kind of weird edge cases does this data structure need to handle? What does our user model actually allow? What kind of thing could be in this file format? And updating your tests and your strategies independently means that you have sort of additive work rather than multiplicative work, right? If you have those shared helper functions somewhere rather than writing them out each time, when you expand one or when you refactor it, it gets picked up by your whole test suite immediately. And that can be a really nice way to test a refactoring, for example, if you generalized something. A couple of patterns for that. One which we've seen here is just write a function which returns a strategy. Those may or may not use the composite decorator that we saw. One underrated strategy is literally just write some global variables. Write out the strategies in detail and just assign them to a global variable that you can use later or import from other test modules. And register type strategy for custom types. Who here has ever indulged in print debugging? Who here likes it more than debuggers? At least sometimes, yeah. If you're doing print debugging with Hypothesis, you might have noticed that it prints every single example, and this gets pretty verbose. So there's two improvements. The first is the note function. Hypothesis.note is basically print, but only during the final example. So this means that you just only see the prints associated with the input that Hypothesis displays for you. Nice little sanity-saving maneuver. And the other one is the event function. This is a little different. In the statistics, when you show statistics, the event function will give you the fraction of test runs that had each distinct value you passed to event. So this can be great to get a sense of what the distribution is. I usually recommend against paying too much attention to distributions, but if it's like 99 to 1 or something, that's worth looking at. If it's just 10 to 1, I probably wouldn't worry. Statistics look something like this. Who saw statistics during the exercises? One person. So if you pass -- hypothesis shows statistics, you will get something like this. It will show you during the generate phase or the shrink phase, how long each test tended to take, how many passing and failing and invalid examples it tried. The invalid ones, for example, when a filter rejected too many times, we'll just throw out the whole example and start over and call that one invalid. How many failures did we find? And then these events. So in this case, 40% of the time, the length of LS was 1, and 60% it was length 2. And we split that out during each phase separately so that you can get a decent sense of what was going on. Settings are a separate thing. They're kind of useful. So a number of people ask things like, how many examples does Hypothesis run? The answer by default is 100 random examples for each test, but that's configurable. You can decide how many you want and just pass that, either as a decorator on the test function, or you can set up settings profiles, where you can determine, for example, am I in CI or not? If I'm in CI, I want a longer, more rigorous one. If I'm locally, I want a quicker run, for example, for local development. And you can select the profile from the PyTest command line as well as setting certain settings from the command line. So the two settings to look at for performance. There's a per test case deadline. By default, that's 200 milliseconds. So most tests, if they're taking longer than that, it's because something unexpected has gone wrong. But sometimes, particularly if you're writing tests that use NumPy or Pandas or Django, it might be totally normal for one of your test cases to take longer than that. So if this triggers, I recommend remembering it's just a warning, right? If you decide that you're comfortable with it taking that long, you know better than a hypothesis about your test suite. And you can adjust that. You can increase it to a larger value or turn it off entirely. And the other one is the max examples setting. How many passing examples should hypothesis find before it decides that it's done with your test? By default, that's 100. This one is a really easy way to make your tests more or less rigorous at the cost of taking less or more runtime, right? If you turn that up to 10,000, you'll be more likely to find bugs, and it will take about 100 times longer to run. So 100, we've found it tends to be a pretty good default for most people. It's rigorous enough that it will find common bugs pretty quickly, while also not taking forever. I've also been asked, you guys are well ahead of the curve here, about determinism. Is hypothesis deterministic? And the answer there is no, it's not deterministic. Hypothesis is deliberately randomized because we have the database to make sure that if we discover any failures, we'll save them and then replay them before doing random generation the next time you run. That means that if you find a bug and your test fails and you run your test again and it passes, you can be confident that it's because you fixed the bug rather than because hypothesis didn't find the same bug again. If you do want determinism though, there is a de-randomize setting, and you can also set the hypothesis random seed from the command line. In both of these cases, I tend to think it can be useful to run in deterministic mode, but you want to separately have a non-deterministic mode to discover new bugs. Question? Periodically. So this is, if you're running a hypothesis regularly over, for example, several months of development, do you want to re-randomize that to change the set of examples it's looking for? Great question. So this is basically my argument against the de-randomize setting. We have it in there for people who really value determinism, but I think that being able to discover new bugs tends to be pretty useful. The other one there is, we'll talk in a moment about, sorry, go ahead. Okay. Yeah, so if you find a bug early on in development, should you continue replaying that forever? Hypothesis will evict database entries if they turn out no longer to trigger a bug. So if you discover a bug and then fix it, hypothesis will replay that for a little while and be like, okay, I guess that was fixed, let me throw that one out. It can make sense to blow away the database occasionally, but it should automatically manage itself just fine. We'll talk more about databases in a moment. This blog post from my colleague Nelson Elhage is really good on two kinds of testing, sort of distinctions between people who use tests as a tool to find bugs, which is in some ways like the natural mode for hypothesis, and people who use tests as a way of checking for regressions during team development. And in that case, you really want a very fast, quite deterministic workload, so you can be confident that your CI system will only ever fail if a bug has been newly introduced rather than just newly discovered. And in that case, it's really important to complement that with a separate system for finding new bugs over time. Hypothesis is designed so that you can configure it to run in either of those modes. Who here uses the random module? Yeah? Randomness is great, but it is also kind of a curse for reproducible tests. So Hypothesis has a couple of tricks to deal with this. The first is just there's a strategy for instances of the random.random class. I would recommend passing one of these around. It's a good practice to make sure that you isolate the state of various parts of your program. But there is also the random module strategy, which will just seed the global random module for if you're using code or calling code that does that. And there is a register random function so that you can add more known instances of the random class that need to be seeded and then reset after each test. This is useful for libraries which maintain their own separate copy, for example. If it is a popular library that's doing this, Hypothesis just has native integration with many of these to manage them automatically. So my general advice is you don't need to think about libraries unless you notice a problem. And if you notice a problem, please open an issue on Hypothesis and we'll fix it. So reproducing failures. I've been talking about the database. One option is just rerun your test and the database will take care of it. And that works great on your laptop locally. Another option is to add an explicit @example decorator. So these ones, they take the same arguments as given, but instead of strategies, you pass the values. And so this is a great way to write regression tests, or as Ryan was mentioning earlier, you can write @example blah 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 .xfail for an example which should cause your property-based test to fail. If those fail, we also have a print blob setting. So this is true for CI systems. And we'll print this kind of base 64 blob so that you can add the reproduce failure decorator and ensure that you can pretty much always reproduce a failure that you had in CI locally. It's kind of awkward, but we are willing to put up with a little bit of awkwardness to guarantee that you never have this problem where your CI system found a failure and you just can't reproduce it locally. That used to happen, and it was really annoying. So it's temporary, but pretty useful. The database, by default, just lives in a local directory. You might have noticed this .hypothesis directory showing up on your local file system. But who here often writes code as part of a team? As many as 10 of us. So if you're working with others, you might want to share your hypothesis database with them so that if anyone's run or a CI run finds a bug, that starts showing up in everyone's tests. And there are a couple of ways to do this. The default is the local directory-based example database, but we also have options like the Redis example database for if you have a Redis server around, or a GitHub Actions cache. So these are systems where you can set up, for example, a profile where on CI you use the shared database, and in local development you use your read-write local database and your read-only view of the shared database. The result here is that if CI finds a failure, and then anyone on your team can reproduce that failure just by running your test locally. It's a remarkably nice workflow. Any questions about the database before I start running through more useful tips? Nope. Okay, let's keep going. So far you've been using hypothesis in sort of random exploration mode. And this is pretty useful, but sometimes targeted or guided search can be more effective. And so the target function does pretty much that. You call hypothesis.target in your test function, and you give it a score that it will try to maximize, and optionally a label. If you want to call it on multiple different things, you need to give it several calls with different labels each time. And then hypothesis will do a sort of hill climbing search to try to find examples that have the largest possible scores. This can be pretty useful for things like target the absolute value of some numerical error from a simulation or a calculation, or try to maximize the number of tasks in this queue that haven't been executed yet, or try to maximize the runtime of this function, or minimize the compression ratio, or even sometimes just balancing, you can pass 1 if it was valid or 0 if it was invalid. This can be a good way to avoid filtering only to valid input if you want to test both valid and invalid, while still biasing it somewhat in that direction. If you don't know what you're targeting, then coverage-guided fuzzing can be a great technique. The idea here is that we start by running random examples, and then each time we find an example that executes a line of code that we haven't seen tested before, we add that example to our pool of known inputs. And as we go on, we start to produce new inputs by trying variations on that pool of existing inputs. And the idea is this lets us get through sort of multi-step criteria much more often than you would expect by chance, right? You have sort of exponential difficulty to make it through multiple conditions, but if you can sort of evolve your way through by local variations, that can be much easier. So Atheris is a library from Google. It's a wrapper for the well-known libfuzzer for Python. It's designed to run a single function for something like hours or even days, sometimes weeks. It's particularly good for C extensions or native code because it can use coverage of native machine code. But Hypothesis integrates really well with this. So this here is in fact a complete integration where we define our little property-based test in the usual way. We call our Atheris setup function, and then we call a theros fuzz. And that will just sit there until you Control-C or otherwise kill the program, trying out new variations over and over again, trying to evolve inputs which do something unexpected. There's also hypofuzz. This is one of my side projects. It's designed, instead of fuzzing one test, to fuzz a whole test suite. So it will use PyTest to find all of your property-based tests, collect them up, divide them between all the cores on your machine, and then do coverage-guided fuzzing of all of them simultaneously. So it'll interleave execution, it will prioritize them dynamically in a variety of ways, and in both cases, both for hypofuzz and also a theros, as soon as a failure is found, it just gets saved to the database in the usual way. So in order to reproduce a failure found by the fuzzer, you just run your test. So if you're planning to leave your tests running overnight to find bugs, I would recommend leaving them running under hypofuzz, or maybe another fuzzer, rather than just using hypothesis itself. That's basically just because there are some design decisions you can put into a long-running fuzzer, which just take like a couple of minutes to really pay off, but then pay off increasingly much over subsequent minutes and hours. Last thing here, I think, is you've all pip installed Hypothesis today. Hypothesis releases pretty regularly. So every pull request to the library is automatically released on PyPI as soon as CI finishes running, because continuous deployment is great. That means we think you should probably just update on a schedule that works for you. That might be weekly or monthly, to make sure that you get any new features or performance improvements or improved error messages that we've put in. Hypothesis takes stability and semantic versioning extremely seriously, and it may not surprise you to hear that Hypothesis is very rigorously tested. But you should still probably pin all your transitive dependencies, just as a good practice. So that's the end of this section of the talk. Going to take some questions now, and then after questions, our remaining time till 5 p.m. will be, you're welcome to hang around and work on further exercises, including for this section, or leave early if you wish. So thanks very much for coming, everyone, and thanks for sticking with us. All right. Any questions about this section? Seems like we answered them. Yep.
Do you find more useful library in a code base that has a lot of data types defined? So like if you're defining like a lot of enumerations and things like that, thinking more about like specific like in Haskell, if you're like defining like types that are based upon like subsets of the integer class or something like that. Is that when it really kind of becomes more useful? You want more property-based testing if you have a highly developed kind of type structure?
Yeah, so for the recording, I'll try to repeat this and to make sure I understand you. If you have a library which defines a lot of its own custom types, so for subsets of possible values or custom data structures, does that make property-based testing particularly valuable? Is that right? Yeah. I think that maybe makes property-based testing easier in some ways, because you can just say, build me instances of this type, and you can register a strategy for that custom type and get it exactly generated each time. So it maybe makes it more ergonomic, but I think property-based testing can be equally useful even if you don't have that, if you're using built-in data types or messier data structures. For example, I mentioned earlier, Black, the auto formatter, has gotten a lot of value out of just saying, give me strings which are syntactically valid Python source code, and I'll check that if I format them twice, it's the same as formatting them once and I don't crash. That's a relatively simple test conceptually. It was kind of a pain in the butt to engineer the strategy to generate arbitrary syntactically valid Python source code. But if you have those custom data types, it will often be more obvious what the properties might be. You know, round trips between them, you can just look at the types and see whether that might be a round trip.
Yeah, so this is a little bit tangential, but I hope related. One thing that is interesting about the testing process is oftentimes when you're writing tests for your code, it's the first time you're really using your code, right? Like writing code is not using code. Once you're actually writing tests and you're like, man, writing tests for this is awful. Guess what? using the code is probably awful. Like, if your code is very hard to test, there's a good chance that your code is hard to use and hard to reason about. So it's actually kind of like your first chance to get like feedback on your own design. Kind of along those lines in terms of if you have a lot of data types or a lot of stateful code that you wish was pure like functional, and you're just like clobbering yourself with these tests, that might be a good signal to iterate on simplifying things. Yeah, I've actually been very surprised by like how informative it is to go through the testing process to improve my design process.
Yeah. So where are the failed cases cached? Hypothesis generates the examples it uses by sort of making random choices with a random number generator, which you can think of as parsing a stream of random bits. So the thing that we need to save is like the underlying byte string, and we stash that in the database. By default, those live in files under the .hypothesis directory in your local working directory. But let's see. You can also store them in Redis or a number of other places. One nice pattern is if you're using something like GitHub Actions, you can cache that database. So subsequent CI runs will also replay from the cache. And then one of the databases we have will automatically download the zip file from GitHub Actions and replay any examples that were found by CI. But yeah, by default, they're stored just on your local file system. Great question. So I've recommended a few times putting the assertions in your code, not just your tests. Is there any penalty for that? So the first is just a logical thing. There will be some assertions which only apply to a subset of inputs, right? So it's not correct to put those in your code. You have to put them in a test where you know you'll only generate those inputs. But more generally, performance is a potential concern, right? If your assertion is very slow and you put it in your production code, then you get a slowdown. Python does have a -o mode, or the Python optimized environment variable, which will skip running assertions. That's why many security linters will say, like, you should not use assertions, because they're thinking of beginners who will often use them to like assert user is authorized, assert user is logged in. And then if you run in Python optimized mode in production, you no longer check those things. So that can be a security risk, right? You've got to make sure that your assertions don't change the behavior of your program, that they only check what your program is doing in some way. But given that, my preference is usually to write assertions pretty liberally, and then if they turn out to be a performance issue, run with Python optimized mode in production. If that becomes complicated, you can also do a similar thing where you have an environment variable that you set during testing and say, like, if I am in testing mode, assert all these things. Yeah, so if you want to check that your code raises a particular exception type, I tend to think that's not really a concern for Hypothesis itself, but for example, there's the pytest.raises context manager, where you can like try whatever except my exception, else assert I expected, whatever. Yeah, so the way I tend to think about this is pytest is a bundle of like two different things. There's the test runner, which lets you select tests, execute tests, find all the tests to be executed, and so on. Hypothesis doesn't do that at all. PyTest also bundles in some things like the raises, context manager, the warns, context manager, fixtures, and so on, which help you write more expressive test functions. And Hypothesis is pretty much purely on that side of things. So Hypothesis will work with PyTest, but it will also work with unit tests. So you could use like assert raises or assert warns, depending on the style you prefer. All right. Yeah. Would there be a clash between PyTest's settings and hypothesis settings? We try pretty hard, like mostly no, because they're configuring different libraries. So yeah, so I usually use PyTest to run my hypothesis tests. In fact, I'm a core dev of both. So from that perspective, I say we, but partly just I try to make sure that they play nicely together, because I know a lot of people use them together. Hypothesis actually ships with a PyTest plugin that improves the integration in a few ways. Hypothesis settings are configurable only through Python code. We decided that it was just simpler to say, like, no, we're not going to read config files, we're not going to look at environment variables. So our PyTest plugin will actually read things like from the command line for you to let you select the profile and so on. But my preferred way of configuring a hypothesis is by having a pytest conftest.py and just calling the hypothesis code in that setup file. Great questions. If that's all of them though, thanks again everyone for coming. Ryan and I will be around here until 5 if you want to keep going through exercises or keep asking us questions. But that's a wrap. Thanks so much.